In this lecture, we discuss the description of fluid flow. The fundamental assumption that we make as far as the type of fluid flow is the fluid is continuous. That is what we call concept of continuum. The concept of continuum of a fluid tells us that there are no cracks, fissures, openings in a fluid. If you take any point in space in a fluid flow, at every point we can describe the characteristic properties of the fluid at that location as continuous functions. That means at every location in space there exists a particle, a fluid particle, which consists of enough number of molecules whose average characteristic property is represented as the property of the fluid itself. That means in space, in a fluid, everywhere there are particles, there are no gaps or fissures. That is what we call concept of continuum. And we also make another assumption that the fluid is isotropic. That means at one location the characteristics are same in all the directions. With this, let us look at how we are in a position to describe a fluid flow. Let us take one simple example. There is a fluid flow like this, and at one location the velocity of the fluid is measured, and the velocity at that location is 1.5 meters per second. After 10 seconds we have once again measured the velocity, and after 10 seconds the velocity is 1.6 meters per second. Now if we try to look at what is the acceleration of the fluid, then the first temptation is to say that acceleration is rate of change of velocity, and hence we say it is 1.6 minus 1.5 by 10, that is 0.01 meters per second square. Friends, let us try to analyze this problem with a different outlook. First place, do we agree with this answer that 0.01 meters per second square is the acceleration of the fluid? The answer is no, certainly not. If you look back the definition of acceleration of the fluid, it is the rate of change of velocity of same fluid particle. Here we have, in the first instant we have a fluid particle defined at that location whose velocity is measured by a probe, a pitot tube let us say, as 1.5 meters per second. In the second instant there is another fluid particle which was previously here, has reached this location. So this 1.6 meters per second velocity is the velocity of the second particle in second time. So in effect this difference of 1.6 minus 1.5 meters per second in 10 seconds is nothing but at this location the change of velocity of two different particles in different times. Mathematically speaking, this particular difference is what is called local rate, represented by a symbol dou by dou t. So wherever we represent the symbol dou by dou t, it means that it is the change of a property at a location of different particles. On the other hand, what you really require here is the rate of change of velocity of the same particle in different times. So now let us, friends, let us define that particular rate as total rate, which also is called material rate. and also substantive rate, which is represented by a mathematical symbol d by dt. Our inability to identify a single fluid particle and then follow it to get its velocity in different time periods, different time intervals, force us to select one location and then measure the velocity of different fluid particles in different times. That means we are measuring the local rate only. We cannot directly measure the total rate of change of any property, be it velocity, be it temperature, or be it pressure. Any of the fluid and flow characteristics cannot be measured directly. So the analysis of fluid flow in this sense is different from that of a solid. In case of a solid, you can attach a speedometer and travel along with it and then record the fluid speed or velocity, whatever be the case. We can't have such facility in the analysis of fluid flow. That's why, friends, what we do is the analysis of fluid flow is slightly different from, or rather totally different from, the analysis of a solid motion. We take what is called a control volume. A control volume, which is a fixed volume in space, that is our region of interest. We select certain control volume which has several openings, so flow can enter this volume and leave this volume. So the property that can be transported through this control volume can be either the mass or the momentum or the energy. So whatever be the nature of transport that takes place, our region of interest is this control volume, wherein something enters and something leaves. So we will be measuring the local rate of change of that property of the fluid within the control volume, and then we try to get what is called the total rate from these measured local rates. Actually, we can have two different kinds of properties. A property of a characteristic property of a fluid which includes the mass of that body is what is called an extensive property. Whereas if a property is defined per unit mass of that particular fluid, it is what is called an intensive or an intrinsic property of the fluid. So when we study this control volume analysis, what we are really studying is the property per unit mass of the fluid. That means the mass of the fixed mass of a body is not our study. If you take a fixed mass of a fluid and then study, which is difficult in case of fluid flow, such an analysis what we call is control mass analysis. Control mass analysis, which involves a fixed mass in space which remains constant. The mass of the body under study is constant. This control mass analysis also is called a systems approach. A systems approach. In case of fluid flow, what we do is a control volume analysis. Now friends, now that we defined the two different kinds of analysis of fluid flow, let us first go to that control volume analysis. In this example, we have taken it as a location instead of a volume. Now the whole job of analysis of fluid flow is to convert this local rate of change of properties to the total rate of change of properties, so that the total rates can be used to describe the dynamics of fluid flow.